So, we read and watch science fiction. We are inspired by stories about interstellar travel, about the exploration and conquest by humans not only of solar system but also of the galaxy. Studying planets around other stars, establishing colonies on distant planets, and then we remember all of this is currently unfeasible in practice, and yeah, it is somewhat disheartening. And the main problem, of course, is the vast distances. Discussions about various options for interstellar travel have been ongoing for a long time. I also had videos dedicated to specific technologies such as photon and warp drives. The possibility of engines that warp space, allowing one to travel from one point in the universe to another faster than light, is not entirely denied by science. However, the practical development of something like that is likely to remain in the realm of science fiction for a long time, if it ever becomes a reality at all. If we talk about not exceeding, but at least achieving the speed of light in a vacuum, this is something that we also physically cannot do. If, however, we were to travel at speeds close to the speed of light, it is physically possible. But firstly, accelerating to such speeds is not easy and requires a tremendous amount of energy. Secondly, traveling at such speeds through interstellar space is accompanied by various challenges. For instance, collisions even with small dust particles could ultimately cause significant damage to the spacecraft, and that's not all. What about generation ships? Well, here it seems that things are somewhat more simple. Building a large ship, not necessarily fast, but capable of steadily reaching a star with generations of people succeeding each other on board, appears to be a plausible concept. It is theoretically possible to make it happen. However, for journeys that would last hundreds or even thousands of years, there are also numerous challenges. These include issues with galactic radiation, resource management, wear and tear on the spacecraft and equipment. But those all are the options that are frequently mentioned when it comes to interstellar travel. But I would like to explore some, let's say, less popular ideas. And one such idea is exactly what I want to talk about today. How about using planets as spaceships? And not just any planets, but rogue planets that are not in orbit around any stars. They are independently roaming through the galaxy. It sounds intriguing, to say the least. But even before I delve into any details, it is quite clear that this is something that is currently beyond our capabilities. The plot of the novel The Wandering Earth is based on a similar idea. However, if we assume that there are hypothetical, highly advanced intelligent civilizations in the galaxy, they could use such a method of galactic travel. And if that were the case, they might leave distinctive signatures that could be detected by us. There is a paper by Irina Romanovskaya on this topic, published in the International Journal of Astrobiology. In such videos where I talk about some semi-fantastical technologies that require certain, sometimes significant assumptions, I always also try to talk about real existing phenomena and objects related to this topic. Today I'll try to do the same. We will discuss not only the methods of interstellar travel on planets, but also various scenarios of how, in theory, this could be achieved, as well as the rogue planets themselves, about their formation, nature, and abundance, and not only about that. My name is Andrei, and this is Cosmos Elementary. Considering that classic methods of interstellar travel don't seem feasible currently, the idea of using entire planets to travel to other stars doesn't seem very simple either. However, it does offer a range of advantages. Let's start by taking a broad look at this idea, and then we'll delve into details. Such a method is considered, for example, as an attempt to ensure that a civilization could survive in the face of an existential threat. For instance, if a star in a system leaves the main sequence and essentially dies. To preserve and attempt to relocate not just a small group of representatives of the civilization, but a significant portion of the population, building a multitude of interstellar arcs is no simple task. However, relocating the entire population, taking a ride on a planet, is a concept that can be considered. But how do we get to this planet in the first place, and why should it take us anywhere? Fact number 1. Rogue planets exist. There haven't been many discovered so far, but they do exist, and in reality there are likely a lot more, which we will discuss in more detail later on. Next, the main problem of interstellar travel is vast distances. But the galaxy is a complex dynamic system. All objects in it don't stay in one place constantly. And they also don't all move the same way. They can have different velocities and trajectories. Some stars even manage to accelerate to the point that they can actually leave the galaxy. As a result, the distances to other stars, let's say from the Sun, are not constant. From time to time, one star may get closer to another. If rogue planets move on their own just like stars, then at a certain moment a planetary system could be approached not only by a star but also by a free-floating planet. So if we time it right and have necessary means, we can send a significant portion of our population to this planet while it's passing nearby. From there they could travel through the galaxy not on a tiny little spacecraft but on an entire planet. A planet can move faster than other stars on average in the galaxy and eventually reach another system. Of course, there are many buts and nuances which we will discuss later, but here are some more apparent advantages of such a method. This paper presents several points. First of all, well, a planet is large. To pull off such a feat, of course, the civilization must be at an advanced level of development, but it's unlikely that they could build a spacecraft that would rival the size of an entire planet. But a planet could provide plenty of space for space travelers. Moreover, to build a spacecraft, resources need to be extracted from somewhere, and a wandering planet can itself be a source of resources which travelers could use. Furthermore, such a planet may have water. Planets can come in various types, and a liquid ocean could exist even on a planet without a star. There was a study discussing the possibility that some planets may retain primary atmospheres of hydrogen and helium. If those atmospheres are thick enough, they can create a greenhouse effect, trap the heat emitted by the planet itself, and maintain a liquid ocean for a long time. Alternatively, a planet could be covered by an icy shell, and the liquid ocean could exist beneath it, similar to Europa and Enceladus. One of the challenges of deep space travel is radiation. Water can be used as protection against radiation. Additionally, a certain level of protection can be provided by the atmosphere and magnetic field, if the planet possesses them. And, well, another not insignificant thing is gravity. With a sufficiently large planet, there is no need to worry about creating artificial gravity. It may differ from the gravity of our own planet, but that is something we could adapt to. It's clear that this option doesn't solve the problem of slow travel. However, if we're lucky and the planet is good enough, in the face of a global catastrophe such as a supernova explosion in the home system, even if such planetary travelers don't ultimately reach other worlds, they can at least survive for a long time. But it's not excluded that they might find a new home somewhere, especially if they learn to control this planet. Again, it sounds like something out of sci-fi, but on the other hand, at least not as crazy as something like the stellar engine, like the Shkadov thruster, where it involves the movement of an entire solar system. If all of this raised even more questions, let's dive into the details. The paper actually describes several scenarios, and the first scenario is the one I briefly described. It involves the use of rogue planets. How close can objects from outside a system get? We can try to estimate this by looking at our own solar system. Small objects, it seems, enter our solar system quite frequently. In recent years, we discovered two, Oumuamua and comet Borisov. We found them only recently, not because they rarely enter our system, but because our ability to detect them has advanced to that point not that long ago. According to some estimates, one interstellar object could enter our solar system every year. However, these are generally small objects. The larger the objects, the less frequently they occur. And of course, we wouldn't want an entire planet to suddenly enter the center of our system, as it could significantly destabilize it, especially since we currently have no intention of leaving our system. But it's not about us. Larger objects, of course, approach our solar system much less frequently. From what we know, the closest encounter of our solar system with another star occurred about 70,000 years ago. There was a study about this in 2015. WISE 07200846, or Schultz star, approached our system. That was a low-mass system consisting of a red dwarf and a brown dwarf. How close did it get to us? Well, currently the closest star to the Sun is Proxima Centauri, which is more than 4 light-years away from us. And according to scientists' estimates, Schultz star was 5 times closer, at a distance of only 0.8 light-years. The Oort cloud, hypothetical cloud of comets around the solar system, probably extends to a distance of 1 light-year in each direction from the Sun, perhaps even more. So, judging by where the gravitational influence of our star still persists, the edge of the solar system is considered to be the edge of an Oort cloud. So it turns out that relatively recently, even when humans were likely already living outside of Africa, in a sense, within our solar system, there was another star, even a binary system. Even if it just passed by, and even if due to its faintness it didn't stand out prominently against other brightest stars, it's still pretty cool. We don't know if rogue planets have approached us as closely as that. However, how often this could happen depends on how common they are. Firstly, where do they come from? There are 2 main scenarios. Stars form through a collapse of a fragment of a cloud of gas and dust, when for some reason there appears an uneven distribution of matter in such a cloud. A denser region emerges, attracting even more material from the cloud. Eventually, this process results in a massive gas ball where nuclear fusion reactions ignite. There are also less massive objects that can be independent, such as brown dwarfs, entities that are not quite stars and not quite planets. They can also form in a similar way as stars. The only difference is that the final object lacks sufficient mass to sustain continuous nuclear reactions in its core. Planets, as we believe, form in gas and dust disks around stars. However, the exact process of their formation is still a topic of discussion. According to the scenario known as the disk instability model, gas giants and disks around stars can in principle form similarly to stars. This occurs due to gravitational instability, not in a molecular cloud, but in an accretion disk around a star. So according to one idea, rogue planets may initially form independently, akin to the stars and brown dwarfs. The resulting object is just less massive, and it has never been part of any planetary system. Yet they could also have initially been a part of a planetary system, much like our Earth and Jupiter are part of the solar system. However, they might have been ejected from the system due to some event. This can occur when the central star in the system dies, either through a supernova explosion or without it. The stability in the system can be disrupted by a passing star, ejecting one of the planets and sending it on an independent journey through the galaxy. Moreover, such events are more likely to occur in stellar clusters, where stars are much closer to each other, leading to more frequent gravitational interactions. It is also possible that both scenarios are at play. Some free-floating planets form independently, while others were ejected from their systems. We can't know the exact number of such planets in our galaxy. Even the number of stars in our galaxy cannot be precisely counted, and estimates vary significantly. Some suggest 200 billion stars, while others propose 400 billion. The current estimate for the number of planets in planetary systems is around 1 trillion. Of course, scientists haven't discovered all of them. They extrapolate based on how frequently we find planets around stars. This estimate has been made despite the fact that, as of today, we have confirmed the existence of just over 5,000 planets. The number of known rogue planets is way smaller. However, it's not because there are necessarily fewer of them. It's just more challenging to detect them. In most cases, we discover regular exoplanets indirectly, as they interact with their parent stars. For instance, by blocking a portion of its light, or causing it to wobble slightly. For rogue planets, these methods, for obvious reasons, do not apply. And so we either have to find young rogue planets that have recently formed and still retain a significant amount of heat from the formation process and haven't cooled down yet. Modern, highly sensitive infrared telescopes are capable of detecting such planets. Another method is gravitational microlensing. When a free-floating planet passes in front of a distant star along the line of sight for an observer on Earth, it briefly amplifies the light from the background star, acting as a lens. The challenge here is that it's hard to make repeated periodic observations because a planet is likely to pass in front of a given star only once. Nevertheless, such planets are being discovered. Some time ago there was news about the detection of the largest group of rogue planets at once. Using data from the VLT telescope and other surveys, researchers found a total of 70 such planets. There have been attempts to estimate how many of them there might be in our galaxy. In 2019, there was a study where the authors estimated that at least 1 in every 4 planetary systems may have lost a planet. The final estimate was 50 billion rogue planets in our galaxy. A year later, in another study, there was estimate suggesting that there could be even more rogue planets than stars in our galaxy. If this is the case, then with a specific planetary system where a hypothetical civilization could live, rogue planets might come into proximity even more frequently than stars. This increases the chances for such a civilization to have the opportunity to escape their system by hitching a ride on a planet. But how could this even happen? Firstly, it's important to note that we are discussing a hypothetical civilization that is far more advanced than us and possesses significant technological capabilities. Furthermore, if this civilization is fortunate and discovers a planet approaching them, much will depend on how close it comes to their system. It may end up inside the Oort cloud of that system, similar to how Scholz star was inside our Oort cloud. However, the concept of inside the Oort cloud is not well defined. In the solar system, the outer boundary of the Oort cloud can extend up to 100,000 astronomical units, which is 1.5 light years. If a planet is found at the outer edges of the Oort cloud, 1.5 light years is still basically interstellar distances. Sure, it's closer than Proxima Centauri, but the distance is still enormous. But the inner boundary of the Oort cloud is only a couple thousand astronomical units away, making it much smaller than interstellar distances. Transporting a large portion of population on spacecraft over such distances would be much more feasible compared to traveling to another star. And there's even a cooler idea in which you won't have to travel even 2,000 astronomical units. In the solar system, there are objects on highly elongated orbits around the Sun. For instance, the dwarf planet Sedna has its closest point in the orbit around the Sun, perihelion, at just 76 astronomical units, while its farthest point, aphelion, is nearly at 1,000 astronomical units. As for one of the most distant known objects, 2015 TJ387, which was initially nicknamed the Goblin, it reaches over 2,000 astronomical units at aphelion, essentially reaching the inner boundaries of the Oort cloud. However, at its closest point, it's only 65 astronomical units away from our star. And you probably already have an idea where I'm heading with this. A civilization wishing to escape its system could reach such an object when it is in the closest region of its orbit. We are currently capable of sending a spacecraft to such distances, as demonstrated by Voyager 1, which is now more than 160 astronomical units away from the Sun. A more advanced civilization could overcome the relatively short distance to such an object and put space colonists on it. And from there, they could further reach more distant regions, up to the Oort cloud, and then migrate to a rogue planet. However, there are many challenges to such a journey. Firstly, travel on such an object would also be very slow. Half of the orbital period of 2015 TJ387 is over 20,000 years. Quite a lengthy journey. But the paper also makes a caveat that a more advanced civilization might try to attach thrusters to such an object, since it is significantly smaller than Sedna. And by using the combination of thrust of these engines and also gravity assists, you can potentially alter the trajectory of the object. Moreover, if the idea to leave the solar system is not just out of idle curiosity, but a question of the survival of the species, we might just have to deal with it. Additionally, of course, there is a question of whether, when traveling not directly on spaceships but initially on an intermediary object, the approach of the rogue planet to this intermediary object would coincide. The chance here is clearly small, but again, there is a possibility of altering its trajectory. The article emphasizes the possibility of detecting such cosmic migrants. If there are many civilizations, not everyone needs to experience such luck. But for some, it might happen, and we could try to detect them. Speaking of low chances, the article also mentions that a highly advanced civilization using astroengineering methods might even attempt to alter the trajectory of a passing rogue planet. Again, it sounds like something from the realm of science fiction and currently beyond our reach, but it's not fundamentally impossible. Another response to the low probability of such a coincidence is not to rely on possibility of a rogue planet coming to us at all, and to create your own rogue planet, to eject an object from your system. Once again, since this happens naturally with the methods of astroengineering, one can attempt to do this on purpose. Why build an interstellar spacecraft when you can just launch a planet into interstellar space? Using Earth might be a bit too much. Even in this fantastical scenario, we might have to choose the object very carefully. If the major planet is ejected from the inner system, it could destabilize the entire system, and others staying in the system may not appreciate it. And the energy required to eject an entire planet is unimaginable. Therefore, it is better to choose something smaller and farther away. For our solar system, the article gives the example of Sedna, which I mentioned earlier. A civilization that aims to undertake such a task could have already colonized its system and spread throughout it, especially if the star in the system has already evolved, requiring them to move farther away from it. So, if such an object is closer to us in its orbit, it shouldn't be a problem for a large portion of the population to fly to it. On an object that has a diameter of approximately 1,000 kilometers, they could construct subsurface habitats and infrastructure and also build an engine capable of generating thrust. Let me remind you once again that we are discussing a hypothetical and highly advanced civilization that might surpass us in development by thousands of years. And then using the thrust of the engine, you can alter the parameters of the object's orbit, making it more elongated. And then, once again, through a combination of engine propulsion and gravity assists, like around gas giants, they could eventually accelerate the object enough to leave their system. By the way, I've already talked about gravity assists in detail in this video. And there you have it. Now we have our free-floating planet. No need to wait or rely on anything, just take matters into your own hands or tentacles or whatever they have. With the help of engines, it's even possible to control such an object and direct it towards a specific planetary system nearby. And in that system, by reactivating the engines, it's even possible to enter an orbit around a new star and start settling throughout the system. Yes, the journey to such a system might take a very long time, but there are many factors at play. Perhaps the stellar population density in that area is higher, the stars are closer, or it leads to a promising neighboring system. And after all, otherwise they would have to travel in a much smaller spacecraft, but this way we have a moon-sized object acting as a spaceship. In the previous scenario, the most unrealistic part was of course the intentional ejection from the system. To make it more realistic, we can once again rely on natural processes. As I mentioned before, objects can be ejected from a system or become gravitationally unbound from their stars when the star undergoes its final stages of evolution. If the object is far enough, when the star enters the red giant phase and beyond, it may leave the system. Knowing the parameters of their system, a civilization can select a suitable object and relocate to it, either using spacecraft or another object on an elongated orbit. They can wait for the right moment and then embark on a galactic journey using the object. The paper describes all of this not just to speculate on some hypothetical scenarios, but to consider that, given that everything I described so far may be practically impossible for us, it's not physically impossible and may be accessible to more advanced civilizations. Therefore, it might be possible for us to detect the signs of such activity in space, because those interstellar travelers could leave characteristic technosignatures. For instance, certain signals that might resemble artificial ones, but originate from regions of the sky where no obvious celestial objects exist. As I mentioned before, detecting rogue planets is challenging, so using such signals could be a strategy for identification. For example, we may not see the planet, but we can receive artificial signals from the area of the sky, certain infrared or other electromagnetic emissions, and other signals. By the way, do you remember the so-called wow signal? The one that for several decades now scientists haven't been able to find a definitive explanation for. From time to time various explanations arise, but they are usually dismissed or rejected and existing ones have problems. So in theory, that very signal could originate from such cosmic travelers on planets. As you probably recall, a strong signal was detected from a specific region of the sky, and despite numerous attempts by scientists, they couldn't detect the same signal again. Perhaps at the time, astronomers were fortunate and the Big Ear telescope happened to capture signals from such a free-floating planet with extraterrestrials on board, well, on the surface. We will never know for sure, but it's indeed an interesting idea. Irina Romanovskaya suggests a different term for the search for such signals. Instead of familiar SETI, search for extraterrestrial intelligence, she proposes SMETI, which stands for the search for migrating extraterrestrial intelligence. In all of the scenarios I mentioned, free-floating planets of course are not the ultimate goal. Yes, especially if the planet is large and can sustain certain conditions for billions of years. However, its internal heat is not infinite, and the resources available on one planet for an advanced civilization are less compared to an entire planetary system. Over the course of many thousands of years of galactic travel, representatives of such a civilization could establish colonies on multiple systems. Moreover, one civilization could embark on journeys to various regions of the galaxy on several rogue planets. Some argue that the vast distances make galactic colonization impossible. However, theoretically, a civilization could colonize a galaxy this way. It would require a significantly advanced level of development, a certain degree of luck, but it could be achieved without relying on concepts like wormholes, warp drives, and the like. They just need to be patient, because it will take a very long time. Additionally, such a civilization spread throughout the galaxy will not resemble the galactic empires or federations from Star Wars or Star Trek. They won't have the ability to jump quickly from system to system or even maintain communication easily. It is possible that such colonies would become autonomous and independent, adapting to new conditions, gradually diverging from their parent civilization. So colonizing the galaxy might be possible without faster-than-light travel or even near light speeds. It just doesn't look the way we usually imagine it. And who knows, perhaps someone is colonizing our galaxy this way right now. Thanks for watching. Links to all of the sources are, as always, down below in the description. If you enjoyed the video, leave a like, comment, subscribe for more videos in future. And if you really enjoyed it, feel free to share this video with your friends, family, and everybody else. Okay, bye.